Welcome to the video. This is the third in our four-part series on debugging ArduPilot code. This video will talk about hardware debugging on the actual autopilot while the code is running on the autopilot using the ST-Link linker. So most autopilots either have pads or an actual debug port, kind of a JTAG type port. Actually, it's a software debugger port, and you connect data and clock and ground to something like an ST-Link plugged into the USB of your computer where you'll be doing the debugger. The OpenOCD talks to this debug hardware port on USB and allows it to attach to the GDB software debugging tool. Okay, the steps to set up the environment is you have to install the OpenOCD software on your computer, build special debug firmware for the autopilot that has the debug symbols included in it, and load it on the autopilot and enable the debug port on the autopilot. Attach the hardware linker to the PC into the autopilot, configure OpenOCD and to start it, and then start up the GNU debugger. Here's a short cheat sheet for some of the command lines that will be used in installation later in the video. One note, recently ArduPilot moved in its master development branch, versions after 4.4, which is currently being released, to use a newer Chibios HAL layer. Unfortunately, the current OpenOCD can't show threads when you're debugging on this firmware based on that. So a patch has been developed to allow this, but unfortunately, when you're using it, you can't show all the local variables. So you may have to switch back and forth if you're working off a master branch type code.
Hello, and welcome to another video about ArduPilot development with Henry and myself. And hi Henry, welcome. So
Welcome.
What we're going to look at today is a bug that Henry found this morning. He was testing out a pull request of mine, and he got this logger stuck thread, right? And he was running on a board. I'll just show what the board is. So this is a QI Tech Zealot H743, a nice little board, and they've even personalized it with ArduPilot dev team on the side, which is very, very cute. Anyway, nice little board. He was flying and to test my PR, and he found he got this stuck thread. And the board's usable, but you just can't do any logging because the logging thread gets stuck. And so Henry reported this to me, and so I then got stuck into debugging it, and it involved using a hardware debugger. So we thought this would be a great opportunity to introduce how to use a hardware debugger with ArduPilot. And so we've got the bug. The first step is to be able to reproduce the bug. And I attached to it, I just set log disarmed. And if you set log disarmed, it starts right into the SD card at boot, and it pretty soon gets into this stuck thread. And stuck thread, there's this code in AP logger file. If I open that up, AP logger file, and stuck thread, that happens whenever from the main thread, whenever the IO thread is not alive for a long enough period of time. And there's this little check where it checks whether the thread hasn't been alive for at least 10 seconds. And if that happens, then you get this stuck thread message. All right. So what I'm going to show is how we're going to debug this. Now, luckily, this particular board has a little bit on the side here. There's a little port. It's probably hard to see in my camera there, but that little port there says, the name on it says SWD, and it's a 4-pin JSD-GH. So that's the software debugging port, and 4-pin means it'll have a ground and a 5-volt, and then an SWDIO and an SW clock pin. So in order to use it with the debugger, what we've got to do is attach a debugger, and the particular debugger I'll use today is this one. There are lots of different debuggers you can use. These are very cheap ones you can get on eBay or Amazon. They're just, a few dollars each, very, very cheap. But there are lots of other
ST-Link.
debuggers. And yeah, it's an ST-Link. This is an ST-Link V2. There are some other nice ones. There's a very nice debugger from that CUAV makes for their boards, which is this one here, and it comes with the correct connector for the Pixhawk 6X. So for example, this is a CUAV Pixhawk 6X, and it's got a little debug ports on the side. It's got two debug ports, in fact. There they are, the FMU debug port and the IO debug port. And those ones are for debugging the two microcontrollers in these boards. There's a main microcontroller, the H743, then there's an F1, which is a separate one. So you can debug either of those with this nice little adapter that's CUAV. This is a ST-Link V3 adapter, so you need a newer version of the software that I'm going to show you if you're using that. But for this particular one, this is an ST-Link V2, and we'll be able to use, any old version of, we'll actually need to use some specific versions for another reason, but I'll get into that in a second.
We might say what the concept of hardware debugging is, that the CPU
very good
provides
point.
provides this facility.
That's right. Very good point. So the STM32 microcontrollers have these debug pins, and a really proper setup would have ground and a reset pin and a SDIO pin, an SD clock pin, and then the voltage pin, the reference voltage pin, 3.3 volts typically. But you can actually get away with just the ground and the clock and the IO. And you can ignore the reset pin. The reset pin's good for being able to break. Even if the chip is locked up, you can hit the reset pin and make it recover. But these little ones don't have that, and this board doesn't have that. It has the minimum number of pins for doing debugging. So the absolute minimum is 3 pins. You need a ground, the SDIO, and your clock. And with those 3 pins, you can do debugging.
You can provide power to the board separately through the USB connector.
Yeah, you normally power it over USB or on battery or whatever. In fact, you can get away without the ground pin as long as you've got some other common ground between the computer that's running the debugging and the flight controller, which could be your USB cable providing a common ground. So what I'm going to do is I'm going to attach, I've got a JST-GH 4-pin breakout cable. And there's a few places that sell those. MRO is a good source. M Robotics, they sell them. You can make your own, of course. And then I've just plugged that into this one here. And the pin out for that SWD port on the side of the board isn't shown in our wiki or on the QOTech site. So, but it's sort of obvious because it's only a 4-pin cable. The ground always has to go in the same spot. Just it's the black one at the other end from the red one. So that gives you the ground, and then the clock and IO have got to be the next 2 pins. So you just try it one way, try it the other, and see which works. So I'll do that now. So I will plug in my little SWD adapter into the side of the board like that, and then I'm going to go and plug it into my USB hub like that. And then what I need to do is I need to start up OpenOCD. Now, so the tool we're going to be using is OpenOCD, right? And that's the software that talks to the ST-Link and then allows, and GDB then attaches to OpenOCD. There are other systems for debugging. There's sort of JLink, and there's all sorts of different systems. This particular one is the one we mostly use in the ArduPilot world. Now,
and you'll
to
probably
use it,
have to install it.
You'll probably have to install it. In fact, I'm going to show you some of the installation tricks because there's a few tricks with versions of OpenOCD and the version of Shibios. So I'll just show you launching it, and then I'll get back to building OpenOCD yourself and then installing it. So you need an openocd.cfg file. Okay, now I've just done that as a symlink. We provide in the tools debug directory in ArduPilot. So if I look in tools debug, there's some instructions, readme, which is probably out of date. Yeah, it talks about the Blackmagic probe, and then it does talk about OpenOCD. But we provide these config files. Here's the one that is suitable for an STM32H7. So it says target STM32H7 dual bank, right? Because the H7s that we use in ArduPilot are dual bank H7s. There's also a generic one for an F4. So if you're on an F4 based board, you would use that one. And so I've just created a symlink there. So I do like this, tools, debug, OpenOCD H7 to openocd.config, like that. And so that means I now have my OpenOCD, and it goes and tries to attach to a H7 debugger, and I configure, it auto-configures using with support for an RTOS, which is a real-time operating system, so SPIOS is an RTOS, and auto just says, hey, you work out what RTOS it is. I could type SPIOS in there, but auto works fine. So it automatically works it out, and I'm saying, go and look for an ST link at the top. All right. So what I'm going to do is, now my particular setup, I haven't bothered to go and set up my device config in the device manager stuff to give me the permissions on the debugger in /dev. So I just run it with sudo. Really, if I was doing it properly, I'd go and set my device stuff so that the device gets owned by either the plug dev user or me, but I'm lazy. I'm just going to do sudo OpenOCD. Okay, now that is not working. Now this is the first little trap you're going to get. So we have, if I grab the parameters of this board, and I've got board options. Now if I go help on board options, you will notice that there is a bit for enable debug pins. So by default, ArduPilot disables the debug pins at boot. And that's because you don't want stray electrical, little bits of pulses appearing on those pins and causing your autopilot to lock up in flight, which we have seen happen. It happened on the ground, but it has happened. So I'm going to set that value to 9. Let's see, so it's now set to 9. And why is this not working quite right? Enable HUD. Timeout setting that. Okay, I am actually, I'm getting timeout setting it, and that's because of the bug. Right, so we can't actually set that parameter. So what I'm going to do is I've just power cycled the board, it'll come up, and when it comes up, I'll set that option quickly, hopefully before the bug happens, but I can show you another way. There you go, now I've got it set, so it worked that time. Okay, great. So now if I reboot with that option set, then we should find that you can attach a debugger. There it is, debugger is now attached. All right, and you can tell it's attached. It said it's found a Cortex M7 RLP1 processor. It's found it at 3-point-something volts, which it's not actually getting from the board. It should be, but we don't have that voltage pin connected. So it's just actually getting it off the adapter. Basically, the adapter is cheating on the voltage and assuming 3.3. And all good. So it's now waiting for GDB connections on port 3333. All right. So now, and in fact, it ended up with an internal error there. Let's just ignore that. That is one of the part of the bug we're chasing. So I'm just resetting the board again now. And great. Okay. And so we can go in here and I'll attach a debugger. Now, just watch what I did there. I ran arm none EABI GDB -x tools debug GDB OpenOCD. Now, if we have a look in tools debug, you will find there is this file, GDB OpenOCD.init. That is a GDB initialization file, and that tells GDB to attach to a remote debugger at port 3333. And there you will notice that OpenOCD is listening for debug connections on port 3333. And that's why we need that config. It also sets up some breakpoints on panic and that sort of thing. All right. So when I run that command, I have to give it that special initialization script for the debugger. And then I also have to point it at the binary, the exact binary that's on the board, which in this case is build QOTechZealot bin ArduCopter. Great. So now we're attached. We can sort of go and have a look at what's happening. And now we can't do an awful lot yet because we haven't built with debug symbols. So now what I'm going to do is I'm going to build with debug symbols. So when I configure the board, I'm going to configure it as a QOTechZealot. I'm going to add debugging, and I'm also going to do enable asserts. That means if there's any violations of the Shibios API rules, for example, not taking a lock at the when you need one, or calling a function that's not allowed from an interrupt handler, those asserts will trigger and tell us that we've got an API bug, right? So I'm going to configure with that. Then I'm going to upload now with debug symbols, which will be more useful. Okay, so that's building that now. So now what I'm going to do now is, while that's off building, because that's going to take a bit, I'm just going to show you a couple of little things. So versions of OpenOCD. Hardware debugging on STM32 is always an adventure. And the tools like OpenOCD are constantly in flux, and they have to match, to work really well, they have to match the Shibios version. And this is a source of great frustration. There are also bugs in GDB. So often debugging doesn't work properly, right? And you just have to learn the tricks of how to get around it. So in the first trick is I am using this branch PR fix Shibios, which is a branch of OpenOCD, and I've got it on my Tridge OpenOCD. There, I've got my checkout. This is a clone of the upstream OpenOCD, and it's got some changes in it to cope, which is actually a patch from Siddharth. That's his GitHub username, Bug Obliterator. That's one of the ArduPilot developers. So this little patch copes with the different layout of the Shibios data structures in Shibios 22.11. And this is needed to support thread debugging on the newer ArduPilot. So if I was on ArduPilot 4.4 or earlier, I wouldn't use this branch. If I'm on 4.5 or later, which has the new version of Shibios, Shibios 21, I would need this branch, right? So I am on the newer Shibios, and so I need to run, I've checked out that branch for OpenOCD. I need to run Bootstrap.
What's Bootstrap?
Bootstrap is just a script. It's a common for programs that are based on this AC config, this configuration system. It's a bit like WAF, like a very, very primitive version of WAF, and it basically does the configuration. Then it's a two-step process. I have to first of all do Bootstrap and then do configure. It's basically just a little recipe you have to do before you build, right?
So, are you modifying OpenOCD?
That's right. There's a single patch. There's this single patch on top of the standard OpenOCD to add this patch. Now I'm going to build it. I'm going to build it with J8 so it uses all of my CPUs. There it is. It's built. And so that's now got my OpenOCD. So I actually have already OpenOCD. I have two versions installed on my computer. One of them is for Shibios 21. And the other is for earlier Shibios versions, right? Now, I use both because it depends which branch I'm on. And there's another factor. The Shibios 21 one does not allow me to look at variables on the stack, but the non-ShibiOS 21 doesn't allow me to look at threads. So I actually, in a single debugging session, often switch between these two because there is no single OpenOCD version that works for everything right now with ArduPilot, with the 4.5 bleeding edge master release. So I actually need to switch between these two, which I know is
So,
frustrating.
so should we post those two in a convenient place for people that are?
Possibly. They're dynamically linked, so I don't know if they'll work on somebody else's computer, but if they're running Ubuntu 22.04, they'd work. Or I could possibly build static versions of them that might work on more systems. Um, all right, so let's keep going. So what I'm going to do is I'm going to start up OpenOCD ShibiOS 21, which is the one built with this special branch. All right. And it failed to build, and that's because I didn't do a completely clean build. It'll be fast to redo this. And because when you're changing the debug and assert options in ShibiOS, you've got to do a fully clean build. I could have done WAF clean. I just did RM-RF build, which is the same thing. So this will now build quite quickly because I built it before, and it's just going to use Ccache, compiler cache to build it very rapidly. And once this is built and loaded, now just mention, remember I showed you how to set that debug board options to enable debugging? In current ArduPilot master, it defaults to having the debug pins turned on if you build with --debug, which helps if you've got a problem during startup, because otherwise you can't get in to set that parameter because you can't attach to the board. So in fact, I didn't need to set that anymore because it'll default. All right, there it is, ready to load to the board. It's now loading. Wait for it to flash. Great. Okay, and that should start and boot up. There it is, booting up. Great. Okay, so let's now attach the debugger like that, and then do the GDB, that little recipe that I've shown you before. Great. And so now I can do InfoThreads. Remember the commands we looked at for our previous GDB video? And we can look at all the threads that are in ArduPilot on ShibiOS. And there's a lot of them. There's all of these threads running. All right, so we're going to keep going and just let it run, and we'll wait till the bug gets. The bug has already happened. Stuck thread. There you go. This is a lovely bug because it happens very quickly. Sometimes we get bugs that take days to reproduce, but this is a lovely one. Okay, so what I'm going to do is I know I'm getting stuck thread, right? So that means I am in this logger file, stuck thread. Let's have a look what all the threads are doing. And so stuck thread means that the log.io thread, this one here, is stuck. So let's attach to that thread by doing thread 15. You can see the 15 at the front of that thread name. All right, and let's have a look with a backtrace to see what it's doing. Okay, so it's doing a AP file system FATFS. So this is the logger. So the logger is trying to load a file from the SD card. It then tries to do the file system backend load file, which is doing a FATS stat call, which eventually is coming down. And if we wander up a little bit on the stack, you'll see that it is taking a semaphore. So it's this line of code. Remember that Control-XA we looked at in the previous video to bring up the source code? All right. So it's getting this semaphore. So there we are, trying to get a semaphore, and that is blocking. Now, the only reason that could be blocking is if another thread is also trying to get that semaphore. Okay, so let's go down and look at, so it means that we've got, so that function is never returning, right? If I put a break on 220, then it's never going to get there, right? So that we know there it's blocking in that take semaphore. Now it shouldn't be.
To be sure that you'd have to go and see if it made it to 218, though, right? Because it could have been
Uh,
stopping before then.
well, we know that it's on this line at the moment, right? Because that's the backtrace is telling us.
Okay.
Yeah. So we know it got to that line and we know it's not getting to that line. So it's stuck in that. Okay. And we can look at where it's stuck. I'll just actually run it again. This is where you get bugs with the debugger. With the SPI 21 with the debugger, once you hit a breakpoint, you've got to actually, you lose the ability to add more breakpoints, which is very annoying. So you have to keep working around things. Okay, it's back into stuck thread. Right, so let's go and have a look info threads, and we could end up with different thread numbers because we've restarted. So this, the log IO, where's log IO? There it is, it's now thread 5. Okay, so let's do thread 5 and have a look at backtrace. So we know that this thread is stuck waiting for this mutex. Okay, so here we are inside the SPIOS mutex code, which is what ArduPilot calls a semaphore, but it's really a mutex. Close enough. All right, so we know it's getting stuck here. We know that it's saying sheds go to sleep. That's saying that this thread is going to sleep until somebody else gives up that thread. That means there's another thread out there that is using this semaphore. And it should have been giving it up. So that means somehow we've got the other thread is not giving up that semaphore. Now we need to work out who that other thread is because we've got 20, 30 threads in ArduPilot on STM32. So we want to know what the other thread is. Now we can do that by having a look at the owner pointer of this semaphore. So there it is. MP owner is pointing at the storage thread. Okay, so that means the storage thread is the guilty party that is holding this semaphore. All right, so let's now have a look at info threads and let's have a look at what's happening in our storage thread. There's our storage thread, which is thread 17. Thread 17, and have a look at it. So it is also stuck trying to get a lock. All right, so let's have a look at what it's stuck.
Wait a minute. You're going a little fast. Where did you see that it's stuck trying to get a lock?
Well, it's going the same thing. A scheduler go to sleep, mutex lock, mutex lock, mutex lock, acquire bus. So it's trying to get a lock here, right?
Okay.
So that means we've got two threads, both are trying to get a lock. Now, what we're going to look at is now who owns the lock that the storage thread is trying to get, because that might be a third thread, right? We might have a little chain of threads that are all trying to get each other's locks. So let's go and have a look inside here, MP owner, and the owner is thread star and that little number there, which might be a bit hard to read. Let me just raise the font size. So that doesn't tell us it's a storage thread because that must be a dynamically allocated thread. We've got statically allocated and dynamically allocated threads in ArduPilot. So we need to work out which thread that is. We know that the stack pointer is around 300307778. Okay, so how can we work out what thread that is? Now, if we look at info threads, then it doesn't show us the stack pointer in here. But what we can do is go continue, and if I use, the board is up and running, so I can actually have a look in our sys file system in threads, and I can do an FTP get at sys threads.txt and put it out to standard output. And there's a list of all of our threads, and conveniently, this column here is the stack pointer. Okay, now we were looking for a stack pointer. If we looked at where that was, it was 300307778. So let's have a look here if we can find that thread, and that will be that. It's actually, we need to know where the thread is allocated. All right, so we need to, Yes, okay. So what I'm going to do is have a look on that thread and see if that thread, if that, so that is a dynamically allocated. I still don't have that InfoThreads. I still don't have which thread that is. But I happen to know, because I've already been through this, it is in fact the log.io thread. So let's go and have a look at the log.io thread, which is this one here. Where's log.io? Thread 5. So back to thread 5, and let's go up all the way in thread 5 until it starts all the way up to the top of this thread, and there it is, and great. So this is AP logger, this is the IO thread, and I can look up to where that thread gets started, and I can have a look at port thread create and info locals. Right, I need to know what thread this is. When we create that storage thread, let's go and have a look at where we have in APHAL Shibios and storage. And let's have a look at the thread create. Okay. And right, so this, if we have a look at what the function is called, that is in AP logger and is called the IO thread. Okay, so that is, that's our IO thread. I actually wanted the storage thread. Storage thread, where's our storage thread? There it is. It's actually thread 17 after the reboot. So thread 17, and I'll go up in that one all the way to the top. Storage thread. There it is. That's in scheduler. And if I look at the creation of the storage thread, so thread create static, and yeah, it's the log.io. So I already looked at log.io thread info. I'm sorry for jumping around here. Debugging is often like this, and it can be a bit confusing if you're flogging it out. So let's have a look. So back to thread 5, and we'll go up by about 10, where it starts. IO thread, there it is, and AP logger, and we've got IO, the creation of the IO thread. Yes, and we actually don't keep a copy of the thread pointer here. Okay, so I've forgotten exactly how I determined that it was that the two semaphores were pointing at each other's, right? So basically what we've got is one thread asking for a lock, right? The other thread holds the lock, but simultaneously the other thread is asking for a different lock, which is held by the first thread, which is a classic deadlock situation, right? So you've got neither of them can make progress because both of them are waiting on the other thread, but the other thread is itself holding the lock that is needed. So both of them are deadlocked together. So that means both our storage thread, which holds our parameters and waypoints, and our SD card thread, which does our logging, they're both waiting on each other and they're never going to make progress, right? So which means you can't save parameters and you can't access the file system. Okay, so now what I'm going to do is show how I ended up actually finding the bug here. And I'll show you what the bug fix is. So if we go and have a look at the log.io thread, which is thread 5, and so we go down to the bottom. So it is using this code. It's calling this thing called block read in FATFS, which is calling this MMC start sequential read, which is doing this thing called SPI Select. Now let's go and have a look at HAL MMC. So this is deep in the Shibios code. Modules Shibios, OS, HAL, source, HAL MMC, SPI.C, and at line 820, it's doing this SPI Select. Okay, so SPI Select is going and getting a lock. Okay, so it does a lock here when it's trying to access the bus. All right, so so that's trying to lock the SPI bus that this SD card is on. Now, if we go and have a look at the HWDEF for this board, and QIOTech Zealot H743 HWDEF.dat, and we have a look at the SD card that is on SPI2, right? And then we notice that there's another device also on SPI2, which is our Ramtron. So this is our parameter storage. This is our SD card. They're both on the same bus. Now that's fine. It's absolutely fine to have two devices on the same bus. That's normal, right? They've got like 6 or 7 devices on the SPI, or 5, I think, 5 or 6 on the SPI1 bus. Absolutely fine to be sharing a bus between those two, but the locking has to be correct. Okay, now the one where the locking is unusual is this SD card. If we go and have a look at that HAL MMC SPI, SPI Select is a little hook that goes up via this thing called SPI Select hook, and that goes up into our SD card code. That's this little function here, SPI Select hook, and it goes and does, and it takes the semaphore, right, to guarantee it holds the lock. So that's all great. It means that every time we want to use the SPI bus and the SD card, we have to hold that semaphore. All wonderful. But let's have a look at the code path that the Ramtron uses, which is the storage. So as we had a look here, we saw there were 2 devices using this SPI, so the Ramtron and the SD card, both using SPI2. Okay, if we have a look at the normal SPI path for getting the bus, then it does this DMA handle lock, and then it does the acquire bus, right? Aha, so this is a little bit different. So this means that when we're accessing it for the Ramtron, we get the lock on the DMA handle first, and then we get the bus lock. All right, but when we do it on the SD card, it gets the bus lock first, like via this call, right? And then during the transfer, when it actually does the reads and the writes, that then gets the this transfer hook here, right? That gets the DMA lock. Okay, and that means that we're doing things, the 2 different threads are getting the locks. There's 2 locks involved. There's the DMA channel lock and the SPI device lock. And one thread is getting the DMA, then the SPI device. The other one is getting the SPI device and then the DMA, right? That is a classic deadlock. If you've got 2 threads that are getting the locks in different orders, if one of them gets one of the locks and then you get a scheduling change where the other thread takes over, right? Then the other thread gets the other lock, and now it can't make any progress because it's stuck on the first thread, but the first thread can't make any progress because it's stuck on the second thread. All right, that's a deadlock, and that's why we're locking up. Okay, so now we can look at the fix. And so this is a cheating session because I've already got a fix. And what I'm going to do is just show you what the fix is, and it's terribly simple, right? So if we have a look at this change I've made here, I added in this lines here. So I hooked SPI acquire bus to go via a new SPI acquire bus hook, and that is going to get the DMA channel lock first. And then we need a release hook, which goes via this hook, and that's going to release the DMA channel. All right, so we need to add that in Shibios. And so there I've got a little PR for that in Shibios. So if I go and github.com ArduPilot Shibios and have a look at this PR, and this little PR. So very, very simple. This just adds those hooks. Okay, so then we need to implement those hooks in ArduPilot. So here's the PR that fixes it on the ArduPilot side. So it needs to declare these two little bus hooks. Then it needs to implement them like this and make sure it calls the acquire bus function. And the acquire bus function does get the DMA lock. All right, so if we load that, yep, so I'm going to git checkout. This is PR SD card SPI fix and update the submodule. And then I'll reconfigure and upload. Then that will now fix the bug. And that is how you use Hardware Debugger. So, and now as I mentioned, things are a bit chaotic. You will find that there's all sorts of bugs in OpenOCD related to Shibios 21. And so things like looking at local variables doesn't work properly. Once you've set a breakpoint, you can't set another one. If you've hit the breakpoint, all sorts of bugs. And so that's where you need to be able to switch between different OpenOCD versions and slowly work around things. And it's quite common to end up, modifying the code and add sort of ifs in there and breaks like we did in our last session. And I did, in fact, do that for this one. I added in some break code like you suggested in the last session. I put that into Shibios. So now the board is starting up. There it is. And I'll let it sit there for an hour or two and just make sure that it doesn't lock up the storage. So we actually get logging. And so I've got log disarmed here. So if I do a log list, then you can see that I've got a log getting bigger. This log is getting bigger, right? And it's fine. And so I'm not getting any issues with SD card lockup. All right. Now, I know that was whirlwind, and I know that that's going to be hard for people to follow, but at least it gives people a starting point. But learning how to do hardware debugging, it's a bit of an art, and I'm certainly not the best person at it. There are probably people out there who'd watch this video and think, how terrible he doesn't know how to do whatever. But I muddle through and can generally find the issue. So that's how you get started.
Great, thanks.
Okay.
That was helpful. Good introduction to it.
All right.
Let us try to use it somewhat.
Great.
Sometime.
Okay. Thanks, Henry.
Thanks.
And you have a great day. Right.
You too.
Bye.